Does it work?
All right. Okay. Yeah, it seems to be working. This is a take
Fantastic.
three of the introduction for the beginning of this recorded video. Quick update for people watching this recording in the future. My name is Rihanna, and this is the Phys 1A revision from Term 2, 2022. And we'll get started with some past paper questions. All right. So we're starting off with mechanics. And I've got this first question. It's a little bit using energy, a little bit using some friction, all the goings on of mechanics. So this is in the format of a Moodle quiz, which I believe your final will be in the year of 2022. There are also some in the mix here from past papers that were in person, just in case it ever goes back to that. So this first question here, we have a block with mass m sliding along a surface that is friction involved. And it's initially at a distance d away from some spring. It's moving at a velocity, and eventually it's going to come into contact with this spring, and we're given the spring constant. So we want to figure out what speed the block is when it reaches the spring. So from its initial velocity, after it goes the distance of d, when is it going to hit the spring as a result of this friction slowing it down. Then we're going to think about the next stage of motion. How far is the spring going to compress because of this continuing movement of the mass? And then finally, after the spring's being compressed as much as it can be, how much is it going to extend back? And because we're using springs and velocities and masses, these are all the terms that we're going to need to find energy of the block, rather than trying to figure out our kinematic equations or equations of motion. It's going to be a lot easier to just use our conservation of energy equation. The friction part here is going to be a little bit trickier than our standard conservation of energy, but we can work with that. Pun intended, because we will be using work. All right, so part one, just thinking about when the block goes from its initial starting position to this point, or across distance d, really, because we want the start of it to hit the start of the spring. So our total conservation of energy, we want our initial energy equal our final energy. And our initial energy is going to be the initial kinetic energy because of the motion. And we're also going to have some work input from the friction, because we were told it's going to be sliding and we're given a coefficient of friction. And then this is going to equal our final energy. I'll put the K, because our final energy is still just going to be kinetic energy. Our format for kinetic energy is going to be half mv squared. Our work for friction, let's do this off to the side. So we know work is equal to force times distance. We know our friction force is equal to mu k, our static friction coefficient, times the normal force. And then just looking at this block here, if we did a quick free body diagram, we're going to have some mass times the acceleration due to gravity, and then going up we have this normal force. There's no other vertical forces really. We can do some little friction force there just for completion, but basically our normal force is just going to be our weight force. So our work due to friction is equal to mu k mg d. So let's pop that in, and it's going to be a negative value. This friction force this block is doing work to overcome the friction, so it's losing that energy as a result of friction. So it's going to have a minus component on the initial value, because we want our final kinetic energy to be smaller because we lost energy. So this is going to be mu k mg d, and our final kinetic energy, and bf f for final. We can get rid of the massive, they all cancel out. We can get rid of the halves and then put a 2 out the front here. And so we're going to get our initial velocity minus 2 mu k gd is equal to our final velocity squared, and that's really what we want to find. Our final velocity is then the square root of our initial velocity minus the rest of these terms here. And we can pop in those values they gave us in the question. Our mass is 1.7 kilograms. Our coefficient of kinetic friction is 0.489. Our distance is 3.18 meters. And our initial speed is 7.35 meters per second. They're all in SI units, so we don't have to worry about unit conversion. So let's just put that in. This is going to be 7.35 squared minus 2 times 0.789 times 9.81 for gravity and 3.18 for the distance. And this gives me 4.85 meters per second. And that makes sense. It slowed down once it reached this point here. There was no force continuing to push it. All that was happening is it still had this continuing momentum from the initial velocity, and it eventually lost some of that because of friction taking away some of the energy. So this would be 4.85. Part 2, what distance does the spring compress? So now we're at this point here. This is the end of part 1. We want to figure out this next region of motion. How far does that go? And we're still going to be using our equations for conservation of energy. This time it's going to be our initial kinetic energy. This is at the start of the spring, not the start of the entire process, plus the initial potential energy due to the spring, plus the work done from friction, is equal to the final kinetic energy plus the final potential energy. We want to figure out how far the spring goes, and that's going to be the point where the block stops moving, because once it's stopped, it's not going to push the spring in anymore, and there's not going to be any other forces that are causing the spring to compress. So spring compresses at, I guess, at the total length. When our block becomes stationary. So that's going to be when our final kinetic energy is 0. We also started at the initial point just when our block was at the start of the spring, which means our initial potential energy is going to be 0. And yeah, that's pretty much as far as we can simplify that. So our kinetic energy, half mv initial squared, and this is from part 1. We're going to subtract the effect of friction because that still needs to take away from our initial energy. So minus mu k mg, and we're going to call this x now because we don't really know how far it goes. We want to find that x value. And that's just the same format we had from before, except now the distance traveled is x instead of d. And then this is going to equal just our final potential energy, which we know for a spring is going to be half kx squared. And then it's just rearranging to figure out x. So we can times everything by 2 and take it all to the other, to one side. So let's take everything to this side. So 0 is equal to kx squared plus 2 mu k mgx minus mv squared. So 20 by 2 taking to one side. And then I guess we can probably just take this back to the other side, but it's basically just rearranging x. And this will give us x is equal to negative 2 mu k mg plus the square root of everything that was left. Basically, quadratic formula. because we have this equation and it's got an x squared and an x in there. So it's like ax plus ax squared plus bx plus c kind of format. So quadratic formula, just sticking in all those values there over 2k. And then we can put in all our numbers. We know everything in here. Let's close those brackets. I'm not going to write out all the numbers because it's going to be a real mess. But basically, the static friction coefficient, and K was all given in the question. G, we can just use 9.81, and V was from part 1. So solving that, we get X is equal to 0.315 meters. So our initial distance it traveled was like 3 meters over here. Wasn't moving that fast, so it ended up only compressing by like 0.3 meters. So a little tiny bit. And we would just put that in here as 0.315, 3 significant figures. Then the last part of this question was, after being compressed, the spring does work on the block and it extends again. Where does the block come to rest? So this is after it's been compressed at this point. Spring's going to push back and it's going to travel back this way. It might not reach the initial position. It might go further than that. We will see. Once again, we're just going to use our conservation of energy equations. So it's part 3. This time our initial is going to be just after the situation in part 2. So when the spring is compressed. So initial is when spring is compressed at the maximum compression point from part 2. And then final is going to be where it comes to rest. So in this case, we're going to have our initial potential energy, our initial kinetic energy, and then of course our work from friction, and then our final potential energy and our final kinetic energy. We of course want our final potential energy to be 0. So let's get rid of this. Our initial kinetic energy, well, from our previous part here, we said our final kinetic energy was 0, is when it compressed the most. So our initial kinetic energy in this part is going to be 0, where it's just stopped and pushed the spring right to the edge. And so it's only the spring potential energy that's going to be kicking it back. And we also pretty much want our final kinetic energy to be 0 as well. This is when the block will finally come to rest. And so all we have is this initial potential energy and the work from friction, and we're going to see how that balances out to get us our final value for X. So let's rearrange this. This is going to be half kxi squared. In this case, we know how much it's compressed. That is what we found in part 2. It is not an unknown value. And then this is going to be minus mu k and g, and we'll call this capital D, the total distance back to its rest point. So we'll call this D. Doesn't really matter what you call it, because this will just be in your own working out. We'll only see the final answer in Moodle. And we can rearrange this. Let's rearrange this for D. So we'll take one to the other side, and then it's like D is equal to kxi squared over 2 k mg. And this is blah, blah. We can solve that here, but this is going to be the distance from this spot here after it's been compressed back to somewhere in the initial position. I don't know where it's going to be, on this side or this side. So let's say that D is equal to the distance back to the origin, which we know was X from part 2, plus some extra little bit that we don't know which direction it is or how big it is, but that's going to be our ultimate finishing position from this initial origin. So we're going to say this is equal to xi, the distance back to that origin place, plus some other extra bit x. Don't really know what sign that is. And we'll rearrange that. X is equal to kxi squared over 2 uk mg minus xi. We'll put in all those values. Xi is from part 2. So the part 2 answer. All these other values we know, and we end up with x is equal to negative 1.83. And that is the answer for this last part. So the block is going to come back from rest. And it's basically using this convention here. So this was xi back to the origin, and then we went a little bit further using this convention where at the end of the spring, x is equal to 0, and where the block started was negative 3.18. So we ended up somewhere over here, just a bit before the start of the spring, and it's going to be negative 1.83. All right, that is the end of the first question. Briefly check on how everyone's going. Are there any questions so far? Can't really see the chat at this point, so I'm assuming everyone's fine. And then yell out if you have any questions, or I'll check back at the end of mechanics maybe. Let's move swiftly along to the next question. This one is looking at forces and momentum, kind of doing our free body diagram and seeing what happens. All right, so we've got some block that's being held up on a wall by this little wheel pointy thingy with a force F. And eventually we're going to drop a smaller mass onto it and see what happens. But first of all, part I, we're going to look at just the magnitude and direction of the total force extended on the big mass which we're holding against the wall in terms of the variables given. So let's draw a free body diagram. We've got this block M. We know there's going to be a normal force pushing on it from the wall. There's this applied force F. There's going to be a weight force, mg, and there's probably going to be a friction force. Yep, they've told us that we will have to consider friction. So there's going to be a friction force pointing the other way, F friction. It's trying to oppose it falling down, because this is what our block wants to do if it didn't have friction. Then, due to the wall, we're going to have that normal force and the friction force. If it wasn't on the wall, that it wouldn't have a friction force. So the friction force is just because of the particles in the wall interacting with our particles in the object. So it's not just the normal force that's a result of the wall. The wall is also exerting that friction force. And looking at our free body diagram, we know it is in equilibrium. Which means our sum of forces must equal to 0 in any direction. So looking at this horizontal direction, our F frictional force is going to be equal to mass times the acceleration due to gravity. Just as a little side note, F friction is not going to be equal to our coefficient of friction times n, just because the correct formula for that for static friction is that it's going to be less than or equal to, which means, oops, just lost. There it is. Okay, which means we have no idea what the actual magnitude of that is. Oh, I just found a little chat thingy. Could you screenshot the last question? Yeah, sure. I'll go back to that real quick. Any particular point, Nigel? I'll just like hover for a few seconds at each part. So that's question 1. That's part 2. And then that's part 3. And I'll just go up to the question as well. Oh, it got a bit messy there. All right. Is that all good now? Yeah, excellent. All right. All right, so we're not going to be using this unless we're absolutely told we can. We can use it for kinetic friction, or like, yeah, when we're having some relative motion, that's when it's going to be equal to, but when it's static friction, we're not really sure. So trust this, trust our equilibrium of forces more so than our weird friction models. Okay, so that means our total force due to the wall is going to be equal to our friction plus our normal force. Of course, they're acting in opposite directions and force is a vector. So we're going to have to add them up using Pythagoras. It's going to be F squared plus the, let's go normal force squared plus frictional force squared. Of course, using our sum of forces in the horizontal direction, we also see that our normal force is equal to F, the applied force. So this is going to give us F squared plus mg squared. And this is pretty much as simple as we can get it in terms of the variables given in the question. We can also give an angle. Let's redraw these forces. So we have F friction and normal. So we want this total F wall. You can also find this angle of the force going to be the inverse tan of our frictional force mg over our normal force, which is equal to F. Okay, so that's as good as we can get it. The next part is, now that we're dropping a lump of clay on the bigger mass, it's going to move a little bit. We're neglecting air resistance, it sticks to M, and we're going to say how far is it going to slip down before it's going to be in static equilibrium again. So how much does it slip as a result of that increase in, or that combined velocity due to the collision? And then when does that friction force take over again and go, yeah, this is as far as you're going. So you have our block M, and then our little mass M comes down to our initial, and then our final system, we have the two together, and they come down a little bit before coming to rest. So first of all, let's figure out what our velocity is of the little mass when it hits it. So velocity of M right before collision, because we know it's released from rest at some distance d above the mass. Yeah, so initially released at rest from distance d above. And to find our collisions, we need to figure out what the velocity is like immediately before it hits our other object. And we can just use our kinematic equations for that. So we know our v final squared is equal to our initial velocity squared plus 2 times acceleration times distance. We know acceleration is just due to gravity and it traveled a distance of d, and our initial velocity is equal to 0. So our final velocity, or the velocity of m just before collision, is going to be equal to the square root of 2gd, because we know acceleration is g and the distance it traveled just before that point is d. And then we can pretty much just use our conservation of momentum equation. There's not really any other forces that would cause it to not be conserved. We're just ignoring any kind of friction between the objects or air resistance. It's only going to be friction acting for the final system because it's moving. So overall, we can just say conservation of momentum we have our initial is equal to our final. So it's going to be m, our little mass v, plus m, v, big M. Of course, this is just going to be 0 because that's initially at rest. And then the combined mass times the final velocity. Final and this initial. And we're not really given any values, any numerical values to substitute in. So this was a question from an in-person paper. So they really just wanted the working out, not any final numbers. So we'll keep going. We know our initial velocity from before was m. Oops. There we go. M, and we can substitute that into vi root 2 gd equal to these big masses here. And so from that, we can get our final velocity of the two objects together. All right, so now what do we do with this? So just looking back to our object and the forces acting on our object now that we have the two masses, it's still going to be our total weight mass. This is going to be our mg. We're going to have a normal force and the applied force, and then some sort of friction. We still know that our total force, or the force applied, is equal to our normal force because our sum of forces is equal to 0 in horizontal direction. We know it's definitely not going to move off the horizontal direction, so that's always going to be true. We also know that when we're having, like during motion, our object is sliding. So we're going to have our friction force is equal to our kinetic friction coefficient times our normal force. So this time we can use it because we are certain that it is going to be equal to this. It's really only the static one that's a bit sus. And we know our normal force is equal to our applied force. And now we can essentially just figure out what our acceleration is due to this collision. So our sum of forces in the vertical direction is going to be equal to this downwards weight force. Sorry, this should be m plus m. We add up our masses, we do not times them, that's my bad. All right. So this is going to be our, let's go upwards is positive, so our friction force minus our weight force, which is going to be mu kf minus m plus mg is equal to mass times acceleration. Our mass is, of course, m plus m times a, our acceleration, which means my total acceleration is equal to, actually, before I do that, I know it's moving downwards, so I'm going to say that this is our acceleration must also be negative because we're moving downwards. Which means our total acceleration is going to be equal to g minus mu kf over m plus m, little m plus big M. Just rearranging this part here for A. And then we're going to use our kinematic equation again. This is a very long question. So once again, our kinematic equation using velocity and distance says our final velocity squared is equal to our initial velocity squared plus 2as. We just found our acceleration. We want to figure out the point where it stops moving again and how far it slips. So we want to find how far it slips after collision. And this will be due to velocity after collision and acceleration from net force due to our kinetic friction is acting now. Plus our new weight force. So we found our acceleration, we know our initial velocity, we want our final velocity to equal to 0, so let's solve for this. 0 is equal to our initial velocity, which we said was this big term up here. This was equal to m2gd over m plus m all squared plus 2 times our acceleration term, g minus mu k f over m plus m, and timesing it by s, and we want to solve for s. And so rearranging that, eventually it becomes gd over m over n plus 1 squared mu k f over m plus m minus g. It becomes a little bit convoluted, but trust me that it does rearrange to this. Although if you got something like this in the exam, as much of a pain as this would be to write out in the Moodle terms, it would probably still be fine. But this is probably as simplified as you can get it by taking out m's and rearranging it for the different signs. So that is officially the final answer for that. Also in Moodle, they probably would have given you values for this so you can get out a number, in which case you don't have to simplify it, just chuck in all the numbers in your calculator and hope for the best. So yeah, bit of a long question, that one, but hopefully you followed along. Then the last two parts of this question is, what is a conservative force? So this is just throwing you a bit of a bone with a nice easy question. Conservative force, basically a conservative force does no work on a closed loop. And then for this last part, state the condition under which mechanical energy is conserved. So mechanical energy is conserved when non-conservative forces do no work. All right, so that is the end of that question. I'll just give you a sec to take any last screenshots if you would like to. So that's part 1. And then part 2, the first bit of that, just trying to find that velocity as a result of the collision and conservation of momentum. And then the next bit, using our forces again to figure out our acceleration. And then just using that velocity and the acceleration to finally get our value for s. Alrighty. Okay. I might do either rotation or gravity so we can get on to thermal physics and sound waves. Any particular preference between rotation and gravity? Rotation? Yeah, cool. All right, so this question, we have a object rolling down a slope. So it's a cylinder and it's got some sort of mass, some sort of radius, and it rolls down a slope length L with an inclined angle. It starts from rest at the top of the slope, and they've given us the equation for the moment of inertia of a cylinder. So we want to write our expression for rotational kinetic energy in terms of m, r, and v. So all the values that we have. So our kinetic energy due to rotation is typically in the form of half I omega squared. So this is the rotation version of the kinetic energy. The original one is, of course, half mv squared. So we can see some similarities between the two. This is basically our rotational mass, and this is our rotational velocity, or our angular velocity. And yeah, this moment of inertia thing, it's just a mathematical value that tells us how much mass is distributed from the axes of rotation, which affects how easy or hard it is to rotate. If you've ever been on one of those like playground equipment things that like spins around, and if you're standing in the middle, you're like perfectly fine, but if you're on the edge, you're gonna be like swung off like mad. Or like that ride in Coney Island of Luna Park, where like all the kids start in the middle and eventually they just like slide off if they fall too far from the middle. So basically, if you have this like all the mass distributed at the center of the axes of rotation, you're probably going to be fine, pretty easy to rotate around. If it's if it's distributed quite far away from the center of rotation, then yeah, you're going to have some mad rotational energy. Yeah, so basically this is the form, and they've given us the form for the moment of inertia of a cylinder. So I is equal to half mr squared. If you get any other shape in the exam, just like Google the general form, because there is a general form equation for pretty much any shape, rather than trying to derive it using the integral or the sum or something. It absolutely probably exists, unless they give you some really weird shape, but that would be mean. And we also know our rotational velocity is equal to our regular translational velocity v over r, the radius. And we were given v, okay, we're not given v, but they want it in terms of v, its speed, which is just going to be how fast it goes down the hill rather than how quickly it's going to rotate. And so it's just rearranging for this. Our rotational kinetic energy is equal to half times half mr squared times v on r squared. And we can simplify that out. We'll get rid of the r squared at the top and the r squared on the bottom. And we get 1 on 4 mv squared. V. And of course, you'll write that in Moodle as 0.25 times m times v to the 2. So part 2, what is the speed of the cylinder when it reaches the bottom of the slope? So in this case, we're going to be using our conservation of energy again, but we need to consider that we have translational and rotational kinetic energy as a result of the rotation. So that's pretty much the only difference between rotation and regular energy conservation, is we usually always have rotation kinetic energy and translational kinetic energy, and then this is the form of the rotational kinetic energy, and we just have to figure out what our moment of inertia is. The only time when it wouldn't have translational kinetic energy and only rotational would be if the center of mass isn't moving. So the center of mass is fixed and everything is just rotating about the center of mass, then there's no translational kinetic energy or regular kinetic energy, it's just rotational. But if the center of mass is moving, then we're going to have our normal kinetic energy plus the rotation. So part 2, our conservation of energy, we want our potential energy because it's going to change height. So our potential energy is due to gravity. And our kinetic energy, let's go initial kinetic energy plus initial potential energy is equal to our final potential energy plus our final potential energy, sorry, kinetic plus potential. It initially starts from rest, so this is going to go to 0. And when we're talking about our potential energy for anything, because it's because of gravity, we're going to need to set a datum. So let's say that this is where our potential energy is equal to 0. So up the top, this is going to be when our potential energy is equal to mu gh, and this is going to be the height above. Okay, so that's final. That means our final potential energy is going to go to 0 because it eventually goes to the bottom of the slope. So our initial potential energy is mgh, and our final kinetic energy is going to be our kinetic final due to rotation plus our kinetic final due to translation. And let's put in some of the dimensions here. So we have the length of the slope L, and we know this is angle theta. So our H value should be L sine theta. So this is going to be mg L sine theta. Our rotational kinetic energy was just what we found in part 1. Let's move that a bit. Equal to 1 on 4 mv squared. And our translational energy, kinetic energy, is just our usual format, half mv squared. And so we can combine that together. We get mg L sine theta is equal to 3 on 4 mv squared. And I can cross out the m's. And this gives me my final velocity is equal to v squared is 4 on 3 gl sine theta. And we can solve that for v. We want this final speed of the cylinder when it reaches the bottom. It's not going to come to rest because it's probably still going to keep going after it reaches the bottom. But basically just putting in all our values for mass, our radius, our length, and the angle. Our equation is pretty much all just a format of that. That gives me v is equal to 7.84 meters per second. So this is the velocity of our center of mass of the cylinder once it reaches the bottom. All right. Then finally, what is the magnitude of the net force acting as the cylinder rolls down a plane? All right, so looking at our cylinder here, we know it's going to have weight force going down, mg, and normal force going up. We're not really sure if there's any frictional force. Probably not, because we didn't account for it in our energy equation. So they're pretty much the only forces acting on it. We have absolutely no idea what the normal force is, because typically we find that by saying, okay, when it's at rest, it's going to, the sum of forces are going to be equal to 0, and then we can solve for normal force. But we know it moves, we know it accelerates, so we can't use that. So our total force is equal to mass times acceleration, Newton's law. We have no idea what our sum of forces is. So we can actually look at it from the other point of view and find our acceleration at the bottom of the slope and times it by the mass of the object. And we can find our acceleration by just using our kinematic equations. So we don't know forces. Let's find acceleration. And this will be due to kinematic equations. And it's just going to be v squared is equal to u squared plus 2as. We know it started from rest, so this is 0. So our acceleration is equal to v squared over 2l. And our force is, of course, equal to mass times acceleration. So it's going to be mass times v squared over 2l. And we'll put in our term for v squared that we had before. So our force is going to be equal to mass times 4 on 3 gl sine theta, all equals v squared over 2l. And this gives me a total result for force is equal to 2 on 3 g sine theta times m. And we have all those values, g 9.81, the angle and the mass were given. So the total answer for this ends up as 21.2. All right, that is the end of that question. That was pretty quick. I might move on to thermal physics and waves now, and if we get time, we can come back to the gravity equation, the gravity question. So this was 7.84 and 21.2, and they've given us the units there, so we don't have to worry about that. So just quickly, that is the final question. That is the answer for part 1. That is part 2. And that's part 3. Yeah, it'll fit. All right. Let's move on to thermal physics. So this first one is a pretty quick specific heat one. You'll remember doing a similar thing from the specific heat laboratory with the ice in it. That's pretty much the general form of any of these types of questions in the past paper. It's like if you put two objects together with different temperatures, what's the final temperature, or vice versa. So in this case, we've got someone has really hot coffee at 85 degrees Celsius, and they want to lower that temperature to 50 degrees Celsius, and they're going to do that by putting in ice. And to avoid adding too much liquid to the coffee, they use water ice that has been cooled to negative 100 degrees Celsius. A lot of things wrong here as a coffee drinker, to be honest. But oh well, we'll assume this is the person's like first day on Earth or something. And the general idea is that eventually this ice is going to melt and we're going to have this final combined watery coffee liquid at 50 degrees. We're going to assume coffee has the same specific heat as water, and they've given us the specific heat of ice. So we eventually, I think the difficult part here is figuring out the different stages of ice and the way that they change temperature. So initially we have ice at negative 100 degrees Celsius. So we want Q from change in temperature of ice. Then it becomes ice at 0 degrees Celsius, and that's when it's going to start to melt. So we want this Q here, and this is going to be melting. Then we're going to have water, or the melted ice. Still at 0 degrees Celsius, so this is going to be due to latent heat. And then eventually we're also going to want this third change where we have our melted ice at that final 50 degrees Celsius due to change in temperature of melted ice. And this is all still the same material. So this is the total change for ice. Then for our coffee, we're going to have our initial coffee at 85 degrees Celsius, and we only have the Q there from change in temp of coffee, where we now have coffee at 50 degrees Celsius. So this is our coffee material. So we're going to have 3 terms from the ice and 1 term from the coffee, and all in all, this should all add up to 0 because it's in one closed system. So let's sort this out. We're going to have our Q of ice plus our Q of latent heat of the ice plus Q of melted ice plus the Q of coffee is equal to 0. And this is going to be our, actually, let's do this. Just because that's the order my notes are in. sorry, this is going to be MC, specific heat due to coffee, and the change in temperature due to coffee, plus the same for the ice, specific heat of ice when it's still the ice material that's changing temperature, for the ice, plus MI latent heat of the ice, plus M mass of the ice, but this time specific heat of the water when it's changing temperature. The ice is equal to 0. So this is going to be our 0.3. We're given 300 milliliters. So 1 liter of water is equal to 1 kilogram. So 300 milliliters is 0.3 kilograms. Specific heat of water, 4186. This is going to be initial, final minus initial, so 50 minus 85, plus mass of the ice. How much ice did we put in? That's what we need to find. We need to find how much ice we're putting. I think that's what we want to find. They didn't actually, oh yeah, there it is, how much ice. All right, so MI, we don't know. The specific heat of ice they gave us, it was 1750. And then our change in temperature is final minus initial. It ended up as 0 minus 1. All right. Sorry, minus 100. It started at negative 100. So it ends up being a positive change in temperature. Then we're going to have this latent heat of the ice. So minus, plus mass of the ice again. The latent heat of ice to water is 3.335 times 10 to the 5. And then last but not least, this mass of the ice plus specific heat of water now, because this is after the ice has melted. And this change in temperature is going to be our final minus initial is final minus initial. It went from 0 degrees to 50 degrees final. And that's all equal to 0. We can rearrange this, and what we get is 43953. It's actually minus plus MI 0.717800. Actually, I think the point is equal to 0, and we solve for MI, and that ends up being 0.0612 kilograms or 61 grams. All right, so not too bad of a question. It just has a lot of terms, and we can't forget each of those specific heat changes, or the heat changes as a result of the ice moving through those different phases there. So pretty quick one for that one. Just pretty much the same formula, just for each stage of this heating process. So that's the answer there. And this is kind of the process bit, and then the initial question there. All right, let's move on to the second thermal physics question here. And we have a PV diagram. This will pretty much always come up, so make sure you practice your PV diagrams. Luckily, your exam's online, so you probably won't have to draw one. You had done an in-person exam and you had to draw one, then that's always fun. All right, so we have this thermodynamic cycle, kind of looks like an engine cycle. You'll learn that if you end up doing mechanical engineering. And they've given us the process here. They've told us it's 2.5 moles of a diatomic gas, and it goes through the cycle. So first question, how many degrees of freedom does the diatomic gas have? And give an explanation, what are the corresponding specific heat constants for constant volume and constant pressure? All right, part I. So degrees of freedom, basically the only information we need is that it's a diatomic gas. So diatomic gas is going to have F is equal to 5. And that's how many different unique ways it can move. So we have a diatomic gas, looks something like this. Everything, no matter what it is, it's going to be able to move in 3 translational directions. So we're going to have Y, Z, and X. They're all unique directions. If you moved any way purely in the Z direction, you're never going to be able to explain to me how much you've moved in the Z direction using only X and Y. So they're 3 unique translational directions. So 3 translational degrees of freedom. And then the other 2 for a diatomic gas are rotation. So it can rotate around this way. So it can, if we look at it from like the top, it can be like any of these orientations. And it can also spin around in this other way. So if we're looking at it from the side, it would kind of be the same sort of shape going around like that. So this is side view, and this is the top view. So this is equal to another 2 degrees of freedom from rotation. The reason why there isn't 3, because, you know, we've got 3 different axes, why can't they rotate about each of those axes, is because the third direction of rotation would be around this side. And if we rotate it in this way here, it's going to look the same. So this one is going to look the same for any rotation. So it's not going to be another unique way of moving. So that's why we have 5 degrees of freedom, and we can figure out our specific heat constants as a result of our degrees of freedom. So our constant volume one is equal to, I think it's F on 2 times R, our like thermal physics constant. So this is going to be 5 on 2R. And then our constant pressure is equal to CV plus R. So this is going to be equal to 7 on 2R. All right, that is question part 1. So the next part is calculate the volume at each of the points A, B, C, and D. So what do we already have? We're only given the pressure at the points, each of the points there. We're also given the temperature in some of them, so the temperature at A, B, and C. And we're given the number of moles. So we're going to assume this is an ideal gas. It'd be very rare if they didn't give you an ideal gas. Even then, you could probably argue that everything can be assumed as an ideal gas if you're a theoretical physicist. So we're going to use PV is equal to nRT. So for the volume at A, our pressure is 4.8 atmospheres and our temperature is 200 Kelvin, and we have 2.5 moles. So this is going to be equal to nRT over P, and this is 2.5 moles times my thermal physics constant 8.314 times my temperature was 200 Kelvin, all over my pressure, which was 4.8 atmospheres, and this gives it to me in 8.55 liters. That is just roughly doing some working out. You would probably have to be a bit more careful with your SI unit conversion. So atmospheres to pascals is going to be times 1.01 times 10 to the 5. Atmosphere pressure in pascals. And then you'll probably get the volume out in meters cubed. So to get it into liters, probably Google the conversion because I don't remember it off the top of my head. I think it might be 10 to the -6. But basically they gave us this volume scale in terms of liters. So we're going to give our final value in terms of liters. You can give it in terms of meters squared, but you would have to specify your units. I guess though in Moodle, if they've given you a units, then make sure you stick to that. So I mean, it's probably not a good tactic to teach you if exams go back in person, but Google unit conversion. It's always safest if you're doing online exams. All right, anyway, the volume at part B is pretty much the same sort of process for each of them because they want volume at A, B, C, and D. So B, we've got 400 Kelvin and still the same pressure. So same nRT on pressure, 2.5 times 8.314. This time the temperature, and this should be in Kelvin, 400 over our pressure, which is 4.8 atmospheres. And this gives me 17.10 liters. And then volume at C. This time we're at 2.2 atmospheres and 450 Kelvin. So we have 2.5 moles times 8.314 times 250 Kelvin over 2.2 atmospheres. And this should be 41.97 liters. And then finally, BD. They haven't given us a temperature at point D, but we know that D to A is isothermal, which means the temperature at A must equal to the temperature at D because our change in temperature is equal to 0. So for this one, we're going to be using C was 450 Kelvin. Not 250. I'm not quite sure if that's the right number now, but that's the correct process. So VD, we're using the same temperature as point A, which was 200 Kelvin, and then this is over our pressure at D, which was 2.2 atmospheres. And this gives me my final answer of 18.65 liters. All right, so this is just repeatedly using our ideal gas law and just picking out values from the graph and making sure we take care of our unit conversion. Part 3, what is the work done for the isobaric process from A to B? So A to B is this top line here. Isobaric process, pretty easy to figure out what the work done is. The work done is always going to be the area under the graph in the PV diagram. I guess like more officially, work is equal to the negative integral of P dV. But yeah, this is just an integral, and we know the integral between some points is equal to the area under the curve. So let's figure out what that's going to be. Work integral. But we know our pressure is constant. Which means we can take this outside of the integral. And this just becomes a change in volume. I use this little delta for change in something. And so just putting in our pressure there, our pressure for this part was 4.8 atmospheres at the top of the curve. Up here, 4.8 atmospheres is our constant pressure. And then our volume between A and B, we calculated that here, A and B. This is going to be our volume at B minus our volume at A. And we're probably going to have to do some unit conversions. So times 1.01 is 10 to the 5 the pascals, and then I believe from liters to meters cubed it might actually be 10 to the negative 3 for liters to meters cubed. Yeah, that seems right. which ultimately gives us our total work of negative 4157 joules. And this is the work done on the process to make it expand, which means there is going to be work done by the system, which gives us that negative work value. So yeah, kind of weird. It's like basically an integration. If we've got some line going up like this, then the area under it is equal to our positive integral. We have this negative value out the front of our work equation. It's pretty standard convention, which basically means if our plot is going this way, then the work done or the area under it is going to be negative. But if our plot's going this way, so like on the bottom here, then our work done is going to be positive because we have that negative value out the front. So that's what that negative convention means. Just a mathematical convention set by some old-timey physics people. I think it's a lot easier to figure out, is our thing like gaining energy or losing energy? And then that corresponds to, is work being done on it or work being done by it? And depending on what the question specifies, in this case, it's asked for work done for the isobaric process. So what work is done on the system by some sort of external person, but our gas is actually getting bigger. So our gas will do work to the system, which means there is a negative work being done by an outsider. The outsider gains the work. Yeah, it's some weird naming system, some weird sign convention. So depending on which you prefer, if you've got a decent grasp of, is the gas doing work or having work done on it to be able to figure out the sign convention, or look at the maths, is it going to the right or to the left, and then we'll figure out which way that is. So this is line is going that way, this is line is going that way. All right, part 4. For the adiabatic process from B to C, calculate our change in internal energy. So B to C, this part down here. So IV, our change in internal energy is equal to Q plus W. We don't actually have to do that because we can just find our internal energy straight up. Our internal energy is equal to F on 2R and delta T. And we'll just put in those values pretty much. So our degrees of freedom was 5/2 times our R value 8.314 times the number of moles. And then our change in temperature at point B, it was 450, and our initial temperature was 400. So 450 minus 400, and this gives me 598 joules. Alrighty, and we will have a positive change in energy because our temperature increases. And so our last question, part 5, what is the work done for the isobaric process from C to D? So this is pretty much going to be the same method as part 3 for what is the work done on the isobaric process between A to B, though this time our direction of the cycle is going the opposite way. So from C to D, work is equal to negative P times change in volume. We know this from isobaric process. This time our pressure is 2.2 atmospheres down the bottom, and our change in volume we calculated here. We want these two volumes now. So this is equal to negative 2.2 atmospheres, so times 1.01 times 10 to the 5 the pressure in pascals, then timesing it by our change in volume was 18.65 minus 41.97 times 10 to the negative 3 the volume in meters cubed. And this gives me positive work of 5,197 joules. Cool. So positive work is being done to the gas to make it shrink down, to force it to compress. Just like you probably would have done in the lab with the syringe thing, you had to like physically do work to shorten the volume. But our volume, when we have heat applied, is more than happy to expand on its own and do work to something. We also have this part of the cycle going in this opposite direction towards the right. No, sorry, towards the left. I don't know my left from my right. So in this case, our integral under it is going to be negative naturally, but because our integral for work has a negative out the front, this makes it positive. All right, hopefully that wasn't too convoluted. This paper was from term 2 2019, I believe, and this was just the 1121 version. For the 1131 version of the paper, there was a few extra parts where you had to like find the total energy of the cycle and stuff, but we'll cut it here for the interest of time. All right, so just in case anyone wants to take a screenshot, there's our question, there's our little scribble of how the work is being defined. Part 1 and a little bit of part 2. Just using our ideal gas law, that's pretty much what we're going to be using the whole time for these kinds of questions. And then also that work formula using the integral, and then also our change in internal energy. They're pretty much the only equations that we'll use in the thermodynamic cycles or the PV diagrams. You will hardly ever use some sort of formula for Q, just because it's really hard to be able to pick what Q is in a gas. We can't really use Q is equal to MC delta T, because C is going to be different for constant volume or pressure, just like we saw before. So we'd have a different specific heat value depending on what part of the cycle we're looking at. I think it can be done, but it'd also be a bit complicated. We also don't have a mass, we have a number of moles. So I tend to stay away from this and just use our change in internal energy is equal to Q plus W. You can pretty much find everything just using some version of this, because most of the processes will have one of these is equal to 0. In the rare case where one of the processes has none of them equal to 0, then it might be best to consider our whole cycle, and we know our change in energy for the full cycle is going to be equal to 0. So you might have to find everything and then figure out just that one remaining value there. So that's typically the better method than trying to find Q directly. All right, last 10 minutes of the session. Let's look at waves in a string. Just because the sound question that I prepared was pretty easy. So this question, we have a thin rope connected to a thick rope, and it's got a mass on the end. And a sinusoidal pulse rather is sent along the thin rope. So from here, there's some sort of device that makes it have a wave. And that has an amplitude of 9 centimeters. Yeah, that's pretty much the gist of that. So we want to figure out part 1, what is the speed of the pulse in the thin rope? Then part 2, we have how the power is going to be transmitted when it's reflected, and then also considering the amplitude when it's transmitted. So if we have a wave going through this rope, it's going to hit this boundary, and because it's a lot thicker, some of it will tend to reflect back, but just from I guess general continuity, some of it will continue to move on, just because we have this string part that's like going up and down. So once it reaches here, even though this next part is really heavy to move up and down, it's still going to have some sort of inertia. It's still connected in some way. So this will move up and down, but only a little bit. So that's the general gist of what's happening. Let's get rid of that. So part one, what is the speed of the pulse along the thin rope? Let's just start off with that. And whenever we have some sort of string that's held in tension, and it must be held in tension to be able to transmit a wave, otherwise it's just going to like frolic around like random. Our speed of the wave, B, is equal to the square root of the tension in the wave over our, I believe this should be our density of the wave. So we're given our linear density and we don't have the tension, but we have this mass and we know the value of the mass. And we know just by equilibrium conditions, our tension must be equal to mass times gravity. If we consider this little block here, we know we've got a downwards weight force and then an upwards tension force. And the tension in this string here must be equal and opposite to the tension in this rope up the top, just because if either of these two were bigger than the other, then our string would move towards the bigger force. So yeah, this is our general continuity. I know it's like a little bit weird because we have this angle here. It's hard to tell if it's going to be in equilibrium because they're not in the same direction. But we'll assume we have some sort of reaction force here that makes this true. Cool. So our tension force is just going to be mass times gravity of our object that's hanging over the edge. And then our linear density was given. So our mass was, there it is, 5 kilograms, and our linear density 4.45 grams per meter. Keep in mind the difference between grams and kilograms. So we're going to have to convert one of those. So let's keep that in kilograms. 5.00 times 9.81, and this was 4.45. Yeah, 4.45 grams per meter. So we'll do times it by 10 to the -3 to get it into kilograms. And this gives me my velocity, which is equal to 105. That seems pretty fast. So it's going to be 105 meters per second. Then the next part, half the power is transmitted and half is reflected at the boundary of the thin and thick ropes. So the first part is, what is the amplitude of the reflected pulse? So let's look at our power equation. So for power of a wave, we have half mu v omega squared a squared, and this is just for one-dimensional wave. It's just a wave going through the string. So when we're having our reflected wave, we know our P incident is equal to, half of our P incident is equal to our power of the reflected. And we pretty much have the exact same values here for when we're having the reflected wave, because it's in the same medium, which means we have our same linear density, same speed, and same velocity. Same frequency is what this value is now, and then same wave velocity. So essentially this just boils down to our initial amplitude squared over 2 is equal to our reflected amplitude squared. So our reflected amplitude square root AI squared over 2, and our initial amplitude was 9 centimeters. So this is going to be square root 9 squared over 2, and this gives me 6.36 centimeters. And then finally, part 3 is looking at the amplitude of the transmitted pulse. So same deal with part 3, that our half of our initial power is equal to our transmitted power, but this time we have a different medium. So this time we have our new value of, so mu changes. the frequency stays the same. And we know our tension stays the same. But in our power equation, we have this velocity, which we know is related to the tension. So let's get that out. So V is equal to root T on mu. So let's break down these terms here. So our power is half mu V omega squared A squared for our, let's put this as T for the, no, that's going to look like transmitted. Let's just put this as incident. Omega, or that curly W for frequency, stays the same, so we won't put a little subscript there, but we will for these other ones. Over 2 is equal to half mu transmitted, our transmitted velocity, omega stays the same, and our transmitted amplitude. So let's substitute our velocity equation, our velocity for this equation here. So 1/4 mu incident root T over mu incident omega squared AI squared equal to half mu T square root of T over mu T. Why isn't it right? There it is. Omega squared. We can get rid of these values, they cancel out on both sides. We can probably get rid of the half and just that in there. And we can get rid of the tensions. Sorry, this is going to be half mu I over root mu I times AI squared is equal to mu T over root of mu T A T squared. And I think we pretty much have everything we need to find. We're given our linear density of the thin rope and the thick rope, so we can just chuck those straight in. We don't have to simplify any further. And the amplitudes, and we just want to find our value of AT. So AT ends up being AT squared is equal to half. If you did want to make that a little bit neater, it does boil down to this, but it's a bit of a pain to figure that out. But it ends up being equal to 4.96 centimeters. So you could just put in the values into here, but that's the simplified version of the answers. All right, that is the end of what I have for Phys 1A. So it's 3:30 now, and I'm going to be moving on to 1B in a minute. So if anyone's joined already from 1B, hold on for a hot sec as we get started. So just quickly going through the end of this was 6.36 centimeters, and this was 4.96. So we did see that our transmitted, our initial wave had a amplitude of 9 centimeters, and then most of that went reflected, but some of it also went through a transmitted wave. And yeah, so that's the answers for part 1 and 2. If you want to take a final screenshot there, and then part 3. So let's try get it back up, and I will stop sharing for a minute there. So thank you for joining me for this revision session. I hope it was helpful in some way. I would recommend you just keep practicing past paper questions. On Moodle, there is a folder for past paper questions and solutions for all the in-person ones, and then you can always just redo your quizzes, because there are a lot of questions in the question bank there, and that'll be great practice for you. But yeah, thanks for joining me, and I will see you next time. Well, hopefully not in a 1A revision session. Best of luck for your exam.